Okay, very good morning, everyone.
Good
Yes,
morning, sir.
yeah. Today we are going to discuss about tree. In that, we have to discuss about binary search tree, and we have to go for what is AVL tree and what are the operations we have to perform on AVL tree. It is a self-balancing tree. Mainly, our focus is on this one. Okay, in the last semester, we already covered these two things, but again, I am going to tell you what is tree initially and what are the terminology we have to discuss, and then what is BST and what are the operations based on the BST. Okay, first of all, what is a tree here? Tree is going to be like this. For example, a node is like this. And in the linked list, we created a single node and it contains two different parts, right? It contains two different parts. One is the data node and the next one is the address of the next node. Okay. But here, when coming to the binary trees, for example, trees means binary trees, it is divided into three different parts like this. Okay, for example, there is a node A, for example, I'm writing a simple tree here like this. Okay, it is a simple tree. Here, A is this node, B is a node, D is a node, and everything is a particularly a node. A node consisting of three parts. The middle one is data or value. Okay, and this one is left pointer, and this is going to be the right pointer. This is going to be the right pointer. Or else it indicates left pointer indicates left child, right pointer indicates right child. That means here I am going to store another node. Here I am going to store another node like this. Here also I am going to store another node. For example, B and C. We are representing with this circle like this, for example, but it contains three parts always. Okay, what is that? It is the data and left pointer and the right pointer always. Okay, and here, for example, if in the linked list, it is always represented only one pointer is there. That is going to be a head only, na head. With the head only, we are doing insertion, deletion, searching, everything. Everything is done with a single pointer. For example, if it is a stack, we are going with the top, only one pointer. For example, if it is queue, front and rear, like that in tree it is a binary tree, AVL tree, red black tree, whatever the tree it is, we are always we are always access or discussed or inserting, deleting everything that is going to be happened with the root node only. We are going to be store the address of the root node value in the variable called root. Only one variable. For this root node, everything is connected. Okay, the first node is called root node. Okay, and here the last nodes, that means this last nodes which has no children. For example, A has the two children, B and C. Okay, these are the kids. For example, A is the A is the father of B and C. Okay, here if you observe D, E, F, and G, they have no children. No children, right? These are called leaf nodes. These are called leaf nodes or external nodes. Okay, and these are called internal nodes. These are called internal nodes. Okay, if I am talking about internal nodes, the internal node means these are internal nodes. These are external nodes or leaf nodes. Is my screen is visible, right, everyone?
Yes.
Yes,
Yes,
sir.
sir.
Okay.
Yes, sir.
Okay. Yes, these are leaf nodes and these are going to be the internal nodes. For example, now again, and B and C are siblings. We have to know the terminology. B and C are siblings. Why? Because B and C has the same parent. B and C has the same parent. Okay, B and C has the same parent. That's why B and C are called siblings here. Okay, the terminology which is useful to the red black tree also. I'm telling everything here. Okay, for example, now C is uncle of D. Okay, I'm not telling any blood relations concept here. Okay, here C is the uncle of D. Okay, why? Because here B is the parent of D and B and C are siblings. Then C is the uncle of D. Like that, parents sibling. Parents sibling. Okay. D's parent is B and its sibling is C. Then it is called uncle. Okay. Like that. Who are
Yes,
B's
sir.
nephews? There is no female gender here. Okay. I'm talking about all the things in male only. Okay. Here, B's nephews is
Sir, that's not fair.
the terminology is like that. The terminology is like that. Okay. For example, I'm telling that uncle, you can treat it as a aunt. Okay, C is the aunt of D. Okay, I will satisfy girls also here. Okay,
Okay, sir.
yes. Here, A is not father. A is the mother of B and C. Okay,
Okay, sir.
siblings B and C are siblings. That is no gender, nothing. If it is male or female, it is going to be siblings only. Okay, here F and G are related to B, right? Here, F and G are nephews. Nephews too. That means siblings, children, right? Siblings, children. Nephew or niece, whatever it is, are to the B. Okay, this terminology we have to know. And this is the level. These nodes are at level 0, and these nodes are at level 1. Okay, these nodes are at level 1. Okay, these nodes are at level 2 here. Level 2. Okay, these nodes are at level 2. For example, level 2 is there. For some nodes are level 2. 2 power 2 is 4. 4 uh, 1 2 3 4 5 6 7. Okay, 2 power 2, that means 2 power 2 plus 1, that is 2 power 3 minus 1 is the maximum nodes. Is the maximum nodes if you observe it. For example, this is level 0, level 1, level 2. That means this tree contains level 2. Maximum is level 2. The height of this tree is going to be a level plus 1. Level plus 1. Then it becomes a 3. Okay? 1, 2, 3. The maximum height is 3. If the tree's height is, for example, h, the total maximum nodes in any tree is 2 power h minus 1 is the maximum nodes. Okay, here how many nodes are there? 1, 2, 3, 4, 5, 6, 7 nodes. 2 power 3 is 8. 8 minus 1 is 7 nodes. Like that. For example, there are some nodes, for example, like this. Okay, this is 7, 8, 9, 10, 11, 12, 13, 14, 15. 2 power 2 power 4 is 16. 16 minus 1, it is going to be 15. That is the maximum nodes in a tree. If the h is 3, if the h is height is 3, 2 power 3 minus 1 is the formula. Do you got it?
Yes, sir.
What is the minimum nodes? What is the minimum nodes? H is the minimum nodes. Okay. For example, there are only 3 nodes. For example, if I consider this one, what is the height of the tree? 1, 2, 3. 3 only. The minimum nodes is going to be h. The maximum nodes is 2 power h minus 1. Clear, everyone? Everything?
Yes, sir.
This is the terminology we have to know. Okay. Then we have to go with the binary search tree. Binary search tree means it is following a property. It is following a simple property. What it is going to be, for example, there is a node, and it has the left and it has the right nodes, definitely. But the left nodes are always smaller than the root node. The right nodes are greater than the root node. This property we have to follow. Okay, for example, this is the root node is 50, for example, and here it is going to be 40, and here it is going to be, for example, I'm writing, okay, 60. Here It is going to be a binary search tree. Why? Because 50 is a root node and the value which is smaller than 50 is in the left subtree and which is greater than 50 that is in the right subtree. Okay, it is going to be follow the same property. What is that? The left subtree values, all left subtree values are lesser than the root node and all right subtree values are greater than the root node. This property we have to follow for all the subtrees, all the tree, not only the first point, not only the first point. We have to follow the whole tree. Okay, for example, I want to insert 30, for example, I want to insert 30. Okay, there are always three operations: insert, delete, and search, and display also. Okay, display is also is there. Okay, total four operations we have to discuss in the total this unit. Okay, insert, delete, search, and display. First of all, insert. For example, I want to insert 30. For example, I want to insert 30. This is binary search tree. Okay, binary search tree. I want to insert 30 and 50 is the root node. 50 is the root node. Okay, 50 is the root node. First of all, we have to take a temp value at root, for example, temp value at root. Okay, we have to check that or else simply we can go normally. I am going to check that is 50 is 30, the new node is 30, right? The new node value is 30. The new node value is 30 is greater than root node or less than root node. What it is? Is it less than or greater than?
Less than.
Less than.
Less than.
That means we have to go for the left pointer. We have to go for the left pointer. There is no need to compare and check with and traverse with the right subtree. Directly we are going directly to the left subtree. Now the temp is moving into this point. Okay. And I am going to take a temp one before it. Okay. Now I am going to compare with now I have to check where I have to insert. Now temp is at 40. I have to go check. This is the subtree now. This is the subtree now. This is the subtree. Okay. Now 40 is the root. Imagine that 40 is the root. Okay. Is 30 is greater than or less than?
Less than.
Less than.
That means definitely 30 is going to be inserted. 30 is going to be inserted. No, 30 is smaller than 40. Yes. Is there any other values? Is there any other values after 40?
No, sir.
No. That means both are empty. Here we have to check. Is there any right node here? Is there any right node?
No.
No. Left node.
No left node. No left
No
node.
left node. Then we have to create a node in the left pointer. In the left pointer, I am going to create like this. Okay. And I have to insert that 30 into the right pointer. That's it. Okay.
Yes, sir.
Yes. Now go with, for example, go with 45. I will go with 45 now. Okay. 45 is the root node. New node. 45. I have to compare with 50 now. Is 45 is greater than 50 or less than 50?
Less than 50.
Less than 50. Then we have to go to the left subtree.
Right.
Left
50
subtree.
is left and 40 is right.
Okay. Then I have to compare with 40. Is 45 is less than or greater than 40?
Greater than.
Greater than 40. Then we have to go to the right part. Is there any right part for the 40 here?
No, sir.
No. Then we have to create a node and we have to link it and we have to insert 45 as a right node of 40. Understand?
Yes, sir.
In this way, we have to insert. For example, I will go with 70. For example, now I go with 70. Is 70 is greater than or less than 50?
Greater than.
Greater than. Then we have to go to the right part. Okay, right part of 50. Okay. If there is no nodes in the right part, then immediately we can add as a right node. Okay. If it is some node is there, we have to check with another node. Now, is 70 is greater than 60 or not?
Yes, sir.
Yes, it is
Yes,
greater
sir, it is
than
greater.
60. Then, is there any right node here? Is there any right node? No.
No.
Then we have to create a node in the right part. Then we have to link it. Then we have to insert 70 as a right node of 60. Understand how to insert it?
Yes, sir.
Yes, sir.
Yes. For example, I want to insert one more value. For example, 55. 55. Where it is going to be insert?
In the right subtree of 50. Right side of 50.
Right side of 50. Then I am going to compare with 60. Is 55 is greater than or less than 60?
Less than.
Less than.
Less than. There is no node at the 60. That's why I have to create a node and I have to link it and I have to insert 55 at this position. Understand?
Yes, sir.
In this way, we are going to be insert the values. Okay. Now, traversing, that means a display. Okay. Traversing, then search, then I go for delete. Okay. In this way, we are going to be insert a node into the binary search tree. Okay, if you observe it, 30, 45, every subtree, this subtree is also following the binary search tree. This subtree is also following binary search tree, right? Every part in the binary search tree has to be follow. The left part is always smaller than the root node. Right part is always greater than the root node. For every part in the subtree also it has to be follow. Okay. Now, we have to display the values. That means a traversal. For example, if it is an array, for example, here there are some index values is there. For every time there is a traversal now, we have to take I value at 0, then I less than n and I plus plus. Just using a for loop, just simply I am going to be print error of I. Just simply, this is the traversal technique, right? This is the traversal technique for the array. For the
Yes, sir.
string, we are also taking the value at 0th index to the last value, we are traversing it. Like that, for tree also we have to traverse it. Okay, there are 4 different ways to traverse it. That is post traversal, post order traversal, pre-order traversal, and in order traversal, and level order traversal. There are 4 different ways. Okay, first 3 are comes under depth first search. These 3 are comes under depth first search, DFS. First 3, post, pre, and in. Okay, the level order traversal comes under BFS, breadth first search. Okay, post order, pre order, and in order, all these 3 are comes under DFS, and level order comes under BFS traversal. Okay.
Yes, sir.
Now, how post order will work? How post order will work? I will display here. Okay. First, post order traversal. First, for every post order means, for example, if you consider, I will draw a small thing here, small tree. For example, this is the root, this is the left. I will write it as a root. Okay, and this is going to be a right. This is going to be right. Post order traversal. That means root is comes after left and right. For example, left subtree, right subtree, then it is going to be root. That's why it is called as post order traversal. First left subtree, then right subtree. Root is comes after the left and right. That's why it is called as a post order traversal. It is, we already know that infix expression, postfix expression like that, na? AB plus. This is post order traversal. The operator comes after the two operands. This is called post order traversal. Like that, like that here also left subtree, right subtree, then root node. Then root node. That is called post order traversal. Pre order traversal means root node, root node.
Comes before
Yes, root node comes before,
left and
then
right.
left subtree and then right subtree. Okay, that is the pre-order traversal. Okay, what is in-order traversal? In-order traversal means that is comes under the middle. For example, a plus b, a plus b. The operator comes middle, right? That's why it is going to be the in-order. Like that, in-order traversal means left subtree, root, and right subtree. This is the three different times. Okay. Now I will work with this one. Not left node, it is left subtree. I am talking about left subtree. L means left subtree. R means right subtree, not only nodes. Okay. For example, now if I consider this part, for example, okay, this part. Here, what is root? Root is 50. Okay. And 40 is the left subtree. Left subtree, not only node. Okay. After left subtree, then only we have to go for the right subtree. Okay. That means this is the left subtree and this is the right subtree. Okay. That means left subtree comes before, then right subtree, then we have to go for the root node. Okay, if I go for left subtree also, I have to follow the same post order traversal property. Okay, first of all, in post order traversal, we have to go for left subtree, then right subtree, then root, right? That's why I am going for the left subtree. Okay, and here, is there any other nodes in the 30? No, everything is no nodes is there. Na? This is the only left part. What is the post order traversal for this one? What is the post order traversal for this one?
30, 45, 40.
Yes, that's it. Nothing else. 30. That means left subtree, right subtree, then root node. Okay, for this part only, I'm talking. Okay. Now, if you observe it, left subtree of 50 is completed. Yes, no other nodes is there now, only three nodes. All the three nodes are covered here. Then, after left subtree, we have to move to the right subtree. Then, these three, how it is going to be?
55,
5,
70,
70,
60.
60.
55, 70, and 60. Okay, this is the right subtree. All the nodes in the right subtree is completed. Then we have to go for the root node. This is the post order traversal. Understand?
Yes, sir.
Yes, sir.
Yes. For example, there is another node. I am going to write another nodes. The possible number is 80, for example. Okay. I am going to write 80 for this one. And I am going to write another node. Here the possible value is 52 or whatever it is. 52, for example, I'm writing 52. I'm writing like this. Now, tell me what is the post order traversal of the given tree.
Sir, 30, 45,
30,
40.
45, 40. No problem with the left subtree here, na? Then
Yes, sir. Then 52, 55,
52,
55,
55,
80, 70.
Sir,
Sir,
80,
52,
yes,
80, 70,
yes, 80, 70,
60,
then 60, then
then
50.
50. Yeah.
Good. Why? Because when coming to this position, this is the left subtree, right? This is the right subtree. This is the right subtree. Total is the right subtree of 50. Then here I have to go to the 55 first. But 55 has a subtree, na? 55 has a subtree. If there is no right part of 55, then 52, 55. If there is another node in the right hand part, then 52 that right part and 55. But there is no right part is for 55. That's why 55, 52 is the left part of 60. Then I have to go for right part of 60. But here there is no left part of 70. That's why we have to go for first of all this left part and then right part. Na? Then I have to go for 80. Then I go for 70. Then I go for 60, then I go for 50. This is the post-order traversal of the given tree. Okay. Now, with the same example, I will go with the pre-order traversal. Pre-order traversal. Pre-order traversal means root node will come first, then left, then right. Okay. Now, the first node is always 50. No doubt about that. Why? Because 50 is the root node. Okay. Okay, 50 is the root node. Then we have to go for left part of the root node. Now, what is the left part of the root node? Left part means 40, 30 and 45. Pre-order means root node left and right. Then it becomes
40, 30,
40,
40,
45.
30 and 45.
45.
Okay. This is the left part. If you observe it, 50's left part is totally completed. Then we have to go for the right hand part of 50. Okay. Now, coming to the 60. 60 is the root of the subtree. That's why I have to print 60 first. Then I have to go for
55, 52.
left subtree of 60. Okay. Then 55 is the root node. That's why I print it. Okay. Then I have to move towards left. Then 52 is the root node. Okay. Then there is no
Yes, sir.
right hand part of 55. Then it is completed. 60's left hand part is completed. 60's left hand part is completed. Then I have to go for right hand part of 60. Right hand part of 60. First, what is the root of the part? That is going to be 70.
70.
70, right? But there is no left hand part. Directly I am going for 80 here. Yes? This is the
Yes, sir.
pre-order traversal of the given tree. Roots come first, then we have to go for left subtree, then we have to go for the right subtree. This is the post-order traversal, pre-order traversal. Okay. Then I have to go for in-order traversal. I think all the concepts is already completed in the last semester, but we have to know how to traverse it. The AVL tree, B tree, and the red black tree. Na? Again, we are recapping it. That's it. Okay. In-order traversal. In-order traversal means root node. Root node will come in the middle. For example, this is the left subtree. Left subtree comes first, then root node, then right part. Okay. Now, first of all, what is the left part? What is the left part? This is the left part. And then what is the in-order traversal of the left part? In-order traversal of the left part.
30,
30,
40, 45.
40 and 45. Okay, root 40 is the root here. That's why it is comes in the middle, and 30 is the left part and 45 is the right part. Okay, then left 50. That is the root node. That is the root node of the entire tree. That's why I go with 50. Now we have to go for right hand part of 50 here. Right hand part of 50. Now come to the 60 here. 60 has again two different parts. Okay, right part and left part. Okay, that means this is the left hand part of 60. then after 60 will print, then right hand part of 60. Okay. Now, what is the in order traversal of 60's values?
52,
52,
55,
55,
60,
60,
Then
70, 80.
70, 80.
52, then 55. If it is a right hand part of 55, we have to print there, but there is no. That's why it is completed. That means left hand part is completed for 60. Then I have to go for root node of that subtree. Then 70
Then
and
70 and then 80.
80.
80.
Why? Because there is no right left hand part of 70. That's why 70 I have to print first. Then I have to go for 80 here. Okay. If you observe it, if it is a binary search tree, if I go for in order traversal, then numbers are in the ascending order. The numbers in the tree are printing in the ascending order 30, 40, 45, 50, 52, 55, 60, 70, and 80. It always goes in the ascending order. Okay, if it is in order traversal. Okay, this is about in order traversal
Yes,
of
sir.
a tree. Then the last traversal technique, that is going to be the level order traversal, and it is BFS, breadth first search. Why I called as post order, pre order, and in order depth first search. It always go and starting to this point and again to the next root node and again go to the next root node. If you observe it, it is going to the depth first. It is going to the depth first. Yes, that's why these three techniques are called as a depth first search. But breadth first search means, for example, if there is a root node, for example, one node, it is connected to the two nodes, for example, and I have to cover these two, then I have to go to the next. That is called breadth first search. That means it is completed what it is, what are the children of that root node, then we have to visit that two, then I have to go to the next. That's why it is called breadth first search. For example, here by level, we have to print. That's it, nothing else. Level by level. Level by level, I have to print. What is that zeroth level values? 50.
50,
50,
In the next level,
40 and
40 and
60.
60. And the next level,
30,
30,
45,
45,
30,
55,
50,
70.
55,
45,
70,
55, 70. Then the next level is
52 and
2,
80.
80.
52 and 80. This is a level order traversal. This is a level order traversal. Yes? Understand?
Yes, sir.
Yes, sir.
Yes. This is about binary search tree traversal techniques. Okay. Traversal techniques. It's four traversal techniques: post order, in order, pre order, and level order. First three comes under depth first search. Last level order traversal comes under BFS. This is the traversal techniques, and that is called displaying the tree, for example. Okay. Then I have to go for searching. How I am going to search a node in a binary search tree. Okay. The search element is going to be, for example, 45. The search element is always going to be the 45. For example, I am taking search element is 45. First, I have to take some temp at this position. For example, temp at this root node. Why? Because root will not move. Na? Root is always locating at the root point only. Temp I am going to take at this position. Now I am going to compare, is the search element is equal to the temp. Is equal to temp?
No.
No, sir.
No, no. If it is equal to the temp, directly we can print that yes, the element is found. That is the best case. Then that is completed in only one iteration. That's why searching an element in a binary search tree, it is a best case order of one. Best case, best case. Okay. And the average case and the worst case, the search operation is order of log n only.
Log in.
Log n only. Why? Because it is not order of n. If it is a linked list, in the worst case and in the average case, we have to check all the nodes. That's why it is going to be a linear data structure. No? That is a linear data structure. That is the difference between a linear data structure and a non-linear data structure. Tree is a non-linear data structure. Why? Because the elements are not in a linear fashion. It is differentially, it is organizing like this. Okay, now I have to search 45. 45 is not equal to 50. Then I have to check, is it greater than 50? Is it greater than 50?
No, sir.
No.
Less than
If it is no, that means there is no need to compare with all these elements, right? That forget about the right subtree. That means 45 is either this subtree or else if it is not found. Okay. Now I am coming. The temp is moving into the left hand part only. There is no need to check in the right hand part. Now I am going to check. Now the search element is 45 is equal to temp. Is 45 is equal to 40?
No.
No, sir.
No. If it is found, just simply we can tell that yes, 40 is found at this position. Okay. But that is not found. Then is 45 is greater than 40?
Yes.
Yes.
Yes, sir.
Yes. Then we have to move to the right part. We have to move to the right part. There is no need to check with the elements of the left part of the 40. If it is 100 elements, every time it is removing. There is no need to compare with some such a type of category elements, right? That's why now temp is coming into this property here 45. Now I am going to check that is the search element and the temp value, that means 45 is equal to 45. Yes, it is true,
Yes, sir.
right? Like this we can traverse a tree to search an element. For example, 100, the search element is 100. For example, the search element is 100. Temp is at initially at always at root node. Initially always at root node. Okay. Now I am going to check is 100 is equal to temp value, that is 50. Is it equal? No.
No.
Then I am going to check is search element is greater than or less than 50. Is it? What it is?
Greater than.
Greater than. Then temp is moving to the right hand part. Temp is moving to the right hand part. Now is the search element, that means 100 is equal to the temp, that means 60?
No, sir. No,
No.
sir.
Is 100 is greater than 60 or not? Yes.
Greater than 60.
Then I have to move to the right subtree of 60. Right subtree of 60. Okay. Now I am going to compare. Is the search element 100 is equal to 70?
No, sir.
No. Is the 100 is greater than 70, right?
Yes, sir. Greater than.
Then I have to move to the right hand part of the temp. After 70, then it becomes 80. Is 100 equal to 80? No.
No, sir.
Is it greater than?
Yes.
Yes. But here, what is the right subtree of 80? That is none.
There's
Null. Yes. Then after this, temp becomes null. Temp becomes null. If temp becomes null, that means the element is not in the list. Understand? That means 100 is
Yes.
not found. 100 is not found. Directly we can declare it. If the temp becomes null, immediately we can tell that yes, the search element is not at all found in the tree. Got it?
Yes, sir.
Yes. This is the way to search an element in a binary search tree. Okay. Then the next one is delete an element. Delete an element. For example, deleting an element in a binary search tree, there are three cases. Everyone clearly understand this concept is related to the AVL trees and this concept is related to the red black tree. Lot of confusion and there is so much scope to understand the concept. Okay, that's why these how I am inserting in the binary search tree, the same operation I will do in AVL tree and the same operation I will do in red black tree also. Okay, if the same delete operation I am performing here, the same operation is happening in AVL tree and as well as red black tree. That's why I am telling again. Okay, there are total three cases is there to delete an element. one is the first one is if for example I am going to deleting a node, the node is a leaf node. The node is a leaf node or node has zero children. Okay, this is the first case. For example, I am going to delete a node. The node has zero children. For example, 30, 45, 52, and 80. Okay. And the second case is if I am going to delete a node, the node has one child. That is the second case. And the third case is the node has two children. This is the three cases. These are the three cases. Okay, I have to cover each and every case here. Okay, if you go red black tree or else AVL tree, the cases are so many. Okay, that's why just concentrate here. These three cases, there are subparts is there for each and every case. Okay, in the next classes, not now. Okay, in the red black tree it is very confusing. Okay, but I will try to explain with a beautiful example to cover and understand every small thing to you. Okay, here the first case, the node has zero children. For example, if the first of all, if I want to delete, the element has to be there. Otherwise, I can't delete it. Okay. For example, 100. Is it possible to delete 100 in this tree? No.
No, sir.
Not at all possible, right? First of all, the node, for example, I am going for the case one, the delete element is, for example, 45. Okay? The delete element is 45, and I have to check again. I have to do the same search operation. If the temp becomes null, then we can't delete it. We can tell that the delete element is not available in the list. Okay, the same search operation again we have to go with the delete operation. It is not a magic. It is not directly going to the 45 and it is not deleting anything. It has to be search. Okay, then temp is at 50. Temp is at root initially. Then it is checking that is 45 is equal to 50.
No, sir.
Then is it smaller or greater than?
Smaller.
Then temp is moving into the left hand part. Now 45 is equal to 40.
No. No, sir. Greater.
It is greater. That's why temp is moving. Temp is moving to the right hand part of 40. Okay. And every time we have to maintain the parent also, then it becomes a temp 1. Okay, this becomes temp 1 and then it becomes a temp 1. This is temp 1. This is temp 1. Okay, now I am checking that is 45 is equal to 40. 45? Yes.
Yes, sir.
It is found. Now it is found. Now 45 has 0 children or 1 children or 2 children. How many children it has?
0. Leaf node. It's a leaf node.
Leaf node. It's a leaf node. No children is there, right? If it is no children, just simply we can delete it. No need to bother about it. That means simply I am writing that temp 1 in direction. What direction it is? Is it right? Right. Temp in direction right is equal to null. That's it. Only single line. Temp 1, the father of temp is a temp 1, right? Temp 1 in direction right node. In what direction we go? In the right direction. Na? That's why temp in direction right is equal to null. That's it. Very simple it is. If it is a child, if it has 0 children, we can simply write it as temp 1 in direction. What direction it is? Is it right or left? If it is 30, temp in direction left is equal to null. If it is 45, I am telling that temp in direction right is equal to null. Then immediately it is deleted. Understand?
Yes, sir.
Yes, in this simple way we can delete it. When it has 0 children. Okay, this is the case. If it is a single child, case 2. For example, I want to delete 55. I want to delete 55 or else 70. Not 80, yeah? 70, okay. Whatever it is, I'm going to delete 55 for example. Again, I have to take a temp at root node and is 55 is equal to 50?
No, sir.
No, no. Then is 55 is greater than 50?
Yes, sir. Greater
Yes,
than.
temp is moving into the right hand part now, right hand part. And again, comparing with is then temp 1 is at this position, okay? Temp 1 is at this position, okay? Now, is 55 is equal to 60?
No.
No. Then, is it greater than or less than?
Less than.
Less than. Then it is moving to the left hand part of this one. Then it becomes a temp 1. Then it becomes a temp 1. Okay. Then it becomes a temp 1. Why it is? It is temp 1. Okay. Now it is temp 1. That means it is a parent. Now, is the delete element that is 55 is equal to temp?
Yes.
Yes. Now, that means we found it and we are coming out of the loop and everything. Then I am going to check that how many children for 55?
One children.
One
One
children. If
child.
it is zero child, simply we can tell that what direction we came in the left direction. Na? Simply we
Yes,
are
sir.
writing that a temp in direction left is equal to null. That is enough. If it is a zero child. But 55 has a single child. Either it is left or right, whatever it is. Okay. Just simply we have to write temp in direction. What direction it is to the parent?
Left.
Left,
Left.
right. Then we have to write a temp in direction left is equal to that child of
Child
55.
of 55.
Then it is going to be like this. Then the link is going to be like this directly. Then the middle part is deleted. It is deleted. Understand?
Yes, sir.
It is deleted like this. Yes. This is how to delete a single child node. Okay. This is the second part. Second case. If I go for third case, if the node has two children, I will check with 50-50. Okay. The node is going to be two children. There are 40 has two children, 60 has two children, and 50 has two children. I will go with 50. The delete element is 50. Temp is always at this node. And is the delete element and the temp is equal or not? Yes,
Yes, sir. Equal.
it is equal. How many children for 50 now? I have to check always. How many children for 50?
2.
Two children. 50 has two children now. 50 has two children. If it has two children, we have to find either in order predecessor or in order successor. We have to find either any one is enough. Any one is enough. In order successor, or in order predecessor. That means in order traversal. What is the in order traversal of this node? This tree? In order traversal of this tree is
30, 45,
tell me
30,
slowly.
40,
30,
45,
40, 45,
50,
50,
52, 55, 60,
52,
70,
55, 60, 70, and
80.
80. Right? This is the in order traversal, right? What is the in order predecessor of 50? 45. Okay?
45,
What is coming before 50? That is going to be 45. What is coming after 50 is 52.
52.
Okay. That means, for example, here the left hand part, the left subtree is there, na? In the left subtree, what is the maximum value? 45.
45.
That with that also we can replace node with the replace root node, or else what is the smallest value in the right subtree?
52.
52. That is the in order successor or in order predecessor. Okay.
Yes, sir.
That means, for example, we have to go either this way or this way, whatever it is. Okay. I will go for always in order successor. Whatever, no problem. Both are same. I will take temp one or temp at right of the tree, and I have to go deeper into this part. Deeper, temp and direction right, temp and direction, sorry, temp and direction left, temp and direction left, temp and direction left. And the final value is the in order successor. Okay. Or else, if I want in order predecessor, just simply I will take temp one at uh, the temp in direction left, and I will go deeper into the temp in direction right. Deeper into the, for example, if there is another, for example, 42 is, for example, 47 is there, just I have to go deeper into the temp in direction right, that is the in order predecessor. Okay. Got it?
Yes, sir.
Then, for example, now I am going to temp one is at this place, for example. Okay. That means that is in order successor. Now I have to copy this value and I have to copy this value to root node. Copy this value to the root node, and we can swap the values. Actually, we can swap the values, for example, then it becomes a 50. Okay. Then it becomes a 50. Okay. Now it is converted into either a zero child or one child. Okay. Now it is converted into either zero child or one child. Understand?
Zero child.
Yes, it may be converted like that. Okay. May be converted into zero child or one child sometimes. Okay. Here it is a zero child. If it is a zero child, we can easily delete in the last cases. Like that we can delete it. Understand?
So it will be converted into one child when it has a right node extra, right? Like in this successor.
Not understand. Come
Like
again.
over here, 52, if 52 had one more node on its right,
Okay, one more. Yes, it is right. That
then
means it is a single child. It is converted into a single child. Then
yes,
55 left child is replaced with that value. Understand?
yes, sir.
That's it. Yes. This is the three different ways to delete a node. When we are deleting, we have to search the node first. Then we have to check that is the node has zero child or one child or two child. If it is a zero child, just simply what direction it came, sir, temp and direction. If it is right or left, simply assign null. That's it. Okay. If it is a single child, if it has a single child, then parent in direction, that right or left, then what the node it has, that is going to be replaced at that position. Okay. If the node has the two children, we have to search the node first. The node has two children, for example, then we have to find either in order predecessor or in order successor. We have to swap these two values. Then it is converted into either zero child or one child case. Then we have to delete by about two cases. Understand?
Yes.
This is about binary search tree. Okay. Okay, boys.
Yes, sir,
Now,
got it.
what is the disadvantage of this thing? Okay, the disadvantages is there. That's why there is an AVL tree and red black tree comes into the picture. Okay. Now, there are some nodes is there. For example, the values are going to be like this. The main advantage of the binary search tree is the purpose is searching the elements only. Search is become fast, then data will retrieve fast. Okay, linear. For example, what is the search operation? Best case, I'm telling that order of n, order of log n, not order of n, order of log n. I'm telling like that. But if the values are in the ascending order or descending order, I have to make a tree. For example, I have to make a tree. Then the root node, the first node is always root node. Then it is going to be 10. then it is 10, then it is 10, then I have to insert, then I have to insert 20, then I have to insert 20. 20 is greater than or smaller than 10?
Greater than.
Greater
Right side.
than, then I have to go for right node, then I have to insert 20 at this position, then the next node is
30.
30. 30 is also
That will be
right.
a skew tree.
That is going to be like this. Okay. For example, if I draw all the values like this, and everything is the right child of the previous node only. For example, if I want to search 90, I have to search all the nodes. It looks like a linked list. Is it clear or not? Is it a linked list or not now?
Yes, sir.
That is the disadvantage. That is the disadvantage. If the values are given perfectly, then we can draw binary search tree very easily. Yes, it works perfectly, no doubt about that. But if the all values are ascending or descending, either it is a right tree or else it is a left tree, then it is not following any binary tree operation. Just simply it looks like and it operates like a linked list. Then the search operation for or the insertion for the deletion, it will take order of n times in the worst case. Understand?
Yes, sir.
This is the disadvantage. This is the disadvantage in the binary search tree. To avoid this, there is a self-balancing trees is there. The self-balancing trees, that is going to be the first one is AVL tree, and the next class I will discuss about red-black tree. Okay. And now, what is AVL tree and what properties it is going to be follow? AVL tree is a binary search tree. First of all, it is not it is not a binary search. It is a binary search tree. It follows the properties of binary search tree. That means left subtree is always smaller and right subtree is always greater than the root node. That property it is going to be follow. AVL tree is a binary search tree. No doubt about that. Okay. And it is a self-balancing tree. It is a self-balancing tree. How it is going to be balanced? The only thing it is a self-balancing tree. Red-black tree is also a self-balancing tree. I always, okay, first of all we will go. What is balance and what is some terminology is related to the AVL tree. I will tell you. For example, there is a node like this. Okay. Like this. And this is 50. And this is 40. And this is 60. Okay. Like this. And there is a small tree, nothing else. There is a small tree. And here, for everything, we have to calculate the balance factor. The word is called balance factor. I always denote with BF. For example, it is going to be balance factor. Okay, balance factor for every node is either -1 or 0 or 1. The at most is 1 and the minimum value is -1. If the balance factor is either -1, 0 or 1, that indicates it is balanced. It is balanced. If it is other than this, for example, or -2 or 2, that means it is not at all balanced. Then we have to do some rotations. We have to do some rotations. If it is either 2 or -2, we have to go for rotations. There are there are two rotations only, left rotation and right rotation. What are the cases? I will explain. Now I have to how to calculate a balance factor. How to calculate a balance factor. That's it, nothing else. For example, here, okay, this is the tree, for example. Now I have to calculate a balance factor for 44 node. Then we have to, what is balance factor means? The height the difference between left subtree height and right subtree height. Got it? Difference between left subtree height and right subtree height. Balance factor means difference of left subtree height, left subtree height, comma, right subtree height. Okay, difference between left subtree and right subtree. Now what is the height of left subtree and right subtree of 44?
0.
0 minus 0, it is going to be 0. Okay, that means it is a leaf node, it is always 0 only. Okay, now coming to the 40. What is the left subtree height?
0.
0. Right subtree height is
1.
0 minus 1. It becomes
Minus 1.
The balance factor for 40 is minus 1. For 60, the balance factor is
0.
0. Coming to the 50, the balance factor is the height of the 50 is 1 and 2. 1 and 2.
1.
The height means we have to go for the depth. The last node, we have to go for the depth node and we have to calculate it. 2 and it is 1.
1.
2 minus 1, it
2
becomes
minus 1 is 1.
1. In this way, we have to calculate balance factor. Got it?
Yes, sir.
Here the values are either 1 or minus 1, 0. Then it is treated as it's a balanced tree. Here, if you observe it, this is a balanced tree. No doubt about that. This is a balanced tree. Why? Because the balance factor for each and every node is either 0 or minus 1 or 1. Okay? Other than this, that may be minus 2 or 2, that indicates it is not a balanced tree. Then we have to go for rotations. Got it?
Yes, sir.
Yes. Now, just leave it. Now there are two different type of rotations is there. Right rotation and left rotation. Okay. I will tell you with a small example here. Okay. What is, with the small x and y values, I will tell you how right rotation will happen, how left rotation will happen. Then it is not very clear. Then I will go with an example. When I have to go these rotations, then it will be clear. First of all, I will tell you with x and y values, then try to understand it. Okay. For example, there is an x, there is a y. Rectangle indicates the value is null, either there is some other value. Okay. Circle indicates it has some value, definitely. Okay. I will delete. Okay. Like this. Right rotation. This is, I am going to write right rotation. I am working with right rotation. For example, the tree is like this. I have to do the right rotation on x. Right rotation on x. For example, I am going to right rotate on x. Right rotation on x. And I am going to give some values. This is the T1. That means subtrees. Okay. This is the T2. It may be null or it has some other value. Either optional, that is. That's why I'm representing with a rectangle. Okay. T1, T2 and T3 is there. Okay. If it is the right rotation on the x, it is converted into like this. Okay, it is converted into like this. It is rotated. Then just imagine it. Just imagine it. Y comes to the first position to the root node. Okay, y is coming to the root node, and x is the child of y. Okay, what happened here? I will write step by step. Y becomes root. Y becomes root. Okay, there is no change in left part of this one. Okay, there is no change in this one, no change in T1. Okay, then there then x is converted as right child of this, right child of this, right child of y. Okay, right child of y. Then T2 is the right child of y now. Before that, then it is converted into left child of x, left child of x. It is left child of x, and x has already T3 now. T3 is also not at all changed. T3 is also not at all changed. This is T2 and this is T3. This is T3. This is called right rotation. Right rotation. Just note it down, everyone. Note it down. Right rotation on X. What happens? Right rotation on X. What happens? Y becomes root. Just observe here. It is rotating in a right way. Y becomes root. Then X becomes the right child of Y. And T2 is the right child of Y. It becomes a left child of X. These 3 points will happen. Understand? Right rotation. With the example,
Yes,
I
sir.
will tell you, it will be more clear at the time. More clear. Maybe like that, na? When we have to explain right rotation, we have to explain like this. That's why I'm writing this one. Okay? This will understand more clearly when I am explaining with an example. You will understand it. Definitely will understand it. But now it is little bit. Some may be understood, some may be not understood. Okay, definitely. I know now. I know student pulse. That's why I'm telling that maybe it not understand. Definitely, I will go with an example. Definitely, you will understand it. This is the right rotation. Then I have to go with left rotation. I will save it. Right rotation. Okay. Then left rotation I'm writing now. And it has like this, and it has like this. Rectangle represents it may be value or null. Okay, it is T1, it is T2, it is T2, and it is T3. Okay, this is either X and this is going to be Y. Okay, and this is going to be the left rotation. This is going to be left rotation on X. Okay, now it is going to be like this. Simply it is going to be rotated in the left direction. Representing, I am representing the arrow mark here. Here it is representing like this. Y becomes the root node. I am writing here. Just understand. Y becomes the root node. Y becomes the root node. And this T3 is not changed. The T3 is not at all changed. The T3 is like that only. No changes. T3 is not changed. Okay. Now X becomes Now x becomes
Y is left child.
left child of y, left child of y, okay, left child of y. Then x t1 is also not changed. T1 is also not changed, and t1 is just simply the left child of x only. This is t1, and but t2, which is left child of y, that is going to be right child of x. That is going to be the right child of x. That is going to be happen. Okay. This is left rotation on x. Understand?
Yes, sir.
Left rotation. Left rotation. Like this. It is going to be happen. Okay. These are the two cases. Just leave it now. Okay. Now, there are total, when we are inserting the data, okay, total there are four cases are there. Four cases. Okay. What are the cases? When the tree is not balanced, okay, there are four cases. If you are inserting, the insert is same as BST. When we are inserting, after the insertion, we have to check the balance factor is correct or not. If the balance factor is not good means it is not -1, 0 or 1. There are total four cases are there. The first case is left case, okay, and the next case is right case, okay. The next one is left case. The last one is right left case. Okay. Total four cases are there. Okay. It's very interesting. Very interesting. Huh? Very interesting. How many cases are there? When we are inserting the data, just simply we follow how to insert a node into the binary search tree. That one only, the same operation. Okay. After inserting that, we have to calculate what is the balancing factor for the nodes. When, if the balance factor is not -1, 0 or 1, then it goes to either any of this case. Any of this case. Based on this, what we have to do? If it is a left case, we have to do right rotation. Okay? Right rotation. If it is a left case, we have to do right rotation. If it is a right case, just simply go with left rotation. Okay? Just simply do one left rotation. That's it. It is automatically balanced. Okay? If it is left right case, first go for left rotation on child, actually, okay, on child, and right rotation on the node, okay, where the balance factor is missing, there we have to do that. Okay, left rotation on child and right rotation on the node. Okay. Then if it is right case, right rotation on child, and left rotation on node. Okay, these are the four cases. If the case is left, we have to do right rotation. If it is right rotation on node, okay, right rotation on node. What is when it happens? If it is a right case, left rotation on the node. If it is a left case, left rotation on child and right rotation on a node. If it is right case, right rotation on child, left rotation on node. Clear everyone, right? I will explain. Everything is messy here, no doubt about that. I know. I will explain each and every case with an example. I already prepared some images for that. Okay, first, if it is not clear also, again I will explain with an example. Okay, now I have to open with the paint. Right case. Open with paint. Okay. This is right case. Okay, right case. What happened here? For example, the tree is this one. The tree is this one already. 10 and 20. Okay, the 10 and 20. I will erase all these things. I will erase all these things. Then you will understand it. Okay. 10 and 20, the value is already there here like this. Okay. Then I have to insert 30 here. I have to insert 30. Where I have to insert 30?
At the right side of 20.
At the right side of 20 only we have to insert. We have to insert here only. Okay, here I have to insert 30 here. Okay, then it is inserted as binary search tree only, no doubt. Then I have to calculate what is the balancing factor of 30?
0.
0, and it is null. Okay, it is null and it is also null. And here what is the balancing factor of 20?
-1.
-1. And what is the balancing factor of 10?
-2.
-2. It is -2. Okay, now the balancing factor is missing at node 10. That is called node. What I am mentioning here, na? Where it is? I am mentioning that rotation on node. Node means this one only. Node means where the
balancing factor is
balancing
wrong.
factor is wrong or missing. Okay.
Missing.
The child of that one is this one. Okay. Now, from the balance, where the balance is missed, in what direction the node is inserted? The node is inserted in what direction? Right?
Right.
And right. Yes? Right direction only, na?
Yes, sir.
It is inserted in right direction from the unbalanced node. Yes, got it?
In rights, right. Okay, yeah. Like in first and then second right.
Right and right.
And
right
okay,
case.
okay.
This is right case. It is a right case. Then we have to do left rotation
Left
on that.
rotation.
Left rotation on that. Okay. Now it is left rotation on 10. Left rotation on 10. Okay. Left rotation on 10. Okay. Now we already discussed about that. Just simply now 20 is the root node. Understand? That
Yes,
means
sir,
this is X, this is Y. Okay.
Yeah.
This is X and this is Y. Y becomes the root node. That means 20 is the root node now. Okay.
Yes, sir.
Then, but if this is T3 is not at all changed. I already discussed. T3 is not changed.
Yes, sir.
T3 may be null or sometimes nodes. That's why here T3 is represented with 30 only. Okay. Now the root node becomes the left child of 20. If you observe it, I already taken the image, na. Just simply I will open it. Left rotation, na. Left rotation. You observe it. It is going like this. Y is the root node and X becomes the left child. And what is the child of Y? What is the left child of Y? It is going to be the right child of X. Like that only, na. Then here the 10 becomes the child, and for the 10 the T2 is not at all changed. Okay. And here the T1 is left child of 20, then it becomes a right child of 10. Understand?
Yes, sir.
If now calculate what is the balancing factor for 10, 30 and 20.
0
0,
for all.
and this is also 0,
Yes, sir.
and this is also 0. In this way, it is going to be balanced. It's going to be balanced. Understand?
Yes, understood.
Yes, this is right case. If it is the right case, we have to go for left rotation. Got it?
Yes, sir.
Yes, I will save and I will close it. Okay. And the second case, I will go. What is the second case? I already discussed with right, then left,
Left, left.
left. I have to open in. Paid. Okay. Now, if you observe it, already 10, 20 and 10, 20 and 10 is already a tree. Okay. Now the new node is 5. I inserted 5, yet left a child of 10. Okay. Now the balancing factor of 5 is 0. The balancing factor of 5 is 0. And for 10, the balancing factor is
-1.
oh, 1 it is.
Sorry.
It
That's
is
it. 1.
it is 1,
Yeah.
and the balancing factor of 20 is 2.
2.
Okay, it is not valid, na? It is not valid in from invalid node. In what direction? In what direction we inserted that? That is left.
Left,
Left. We are inserted. If it is a left, we have to go where? Go for. We have to go for
right.
right rotation on the node. Right rotation on the node. Okay. Then what happened? 10 becomes root node. Okay. Then 20 is right child and 5 is left child. Understand? Like this. This happened. Is simply like this. Is rotated like this. 10 becomes the root node and 5 is left child, and 20 is right child, and this T1 is already with this only, and the right value of T10 it becomes left child of this, like this. Understand?
Yes, sir.
This now the balancing factor, this one is 0, and for this one is also 0, and for this one also it is going to be 0. Understand?
Yes.
In this way it is going to be working on left case. Okay. Then the next one is left and right case. Left and right case. Now, understand here, 20 and 10, already there is a tree. I inserted 15. 15 is the root node. Where we have to insert 15? It is less than 20 and greater than 10. That's why it is going to be inserted at this position. Okay? Got it?
Yes, sir.
Now the balancing factor for 15 is
0.
0, and the balancing factor for 10 is
-1.
-1, and the balancing factor for 20 is
2.
2. That means here not possible. It is an invalid node. Then in what direction the new node is inserted from the unbalanced node?
Left on the node and right on the child.
Right, then it is left and right case. It is left and right case. It is okay. If it is
So left on the child and right on the node.
yes, if it is left right case, what we are doing? Left rotation on child and right rotation on node. Okay. Left rotation on child. Left rotation. Then I'm doing only this part. Why? Because this is the child, na? Left rotation on child. Then right rotation on this one. Okay. First of all, this may be converted into, this is converted into like this. Left rotation, na? Left rotation. Observe that if it is left rotated, 15 is the root node, 15 is the root node, and 10 is the child of 15. Okay. And 20 is as usual, no problem for that. In the first iteration, in the first rotation, it is looks like this. The first iteration, in the first iteration, 15 is moving here and 10 is moving down. Okay, that is the left rotation on the child. Understand?
Yes, sir.
Then after that, this is the rotation first of all initially. Then we have to do right rotation on the node. Then I have to do right rotation on the node. Right rotation on the node. Understand? Now it becomes 15 is the root node, 10 is here, and 20 is here. Now it is converted into like this. Now 15 is the root node. Now 15 is the root node, and 10 is left child, and 20 is the right child. Is it balanced or not now?
Now it's balanced.
In this way, we have to do left and right rotation. Is it clear?
Yes, sir.
Yes. This is a left-right notation. The last one is right left.
Right, left.
Right left. Right left rotation. For example, the tree is like this. Already 20 and 30 is already there. We are inserting 25. We are inserting 25 now. We are inserting 25. Now, what is the balancing factor of 25?
0.
0. And the balancing factor of 30 is?
1.
Balancing factor of 20 is?
-2.
-2. That means here is the invalid thing. Invalid node it is. Now I have to check in what direction the new node is inserted from the invalid node. In right,
Right.
then left.
Yes, sir. Right.
Right and left. Okay. Now it is a right and left rotation. If it is a right and right left case, we have to do right rotation on child, and left rotation on the node. Now it becomes, first of all, we have to do right rotation on this thing only. Okay, this thing. Then we have to go left rotation on 20. First of all, it may be converted into, this part, especially this part 30 and 25 is converted into like this, and it is 25, and this is going to be 30. Got it? And 20 is here only. Okay? 20 is here only. Then this is right rotation on child. Then that means this is the right rotation on child. Then we have to do left rotation on child, left rotation on the node. Then it becomes 25. It is 20 and it is 30. Like this. It is converted into like this. It is 25. And it is 20, and it is going to be 30. It is following BST if you observe it or not. 25 is the root node, 20 is the smallest node which is in the left hand side, 30 is the greater node which is in the right hand side, if you observe it or not. Yes? Is it balanced or not now? All the balancing factors,
It is balanced.
All the balancing factors of the nodes is 0 only. Yes. In this way, we have to insert. Understand?
Yes, sir.
All the 4 cases. These are the 4 cases we have to observe it. Okay. Now, I will go with example. Okay. I will go with an example, big example here. The values is going to be, now it will be more clear to you. Okay. Just understand. If you are not understand up to now also, it will be more clear. It will be now. Okay. 14 and 17 and 11 and 7 and 53 and 4, 13, 12, 8, 60, 19, 16 and 20. It will cover all the cases it will cover. The first value is, what is the first value? The first value is 40. Just simply we have to create a node, and 14 it is. What is the balancing factor now? What is the balancing factor
0.
now? 0. This is going to be represented with root node. This is root node, and the balancing factor is 0. Okay. No problem. It is balanced. No doubt about that, na? Yes. Now I have to insert
Yes, sir.
17. Where I have to insert 17?
In the right side of the phone.
Right side.
On the
Here
right
I
side.
have to. Here I have to insert. Here I have to insert 17, and 17 is inserted here. Okay. Now, what is the balancing factor of 17? It is 0. And what is the
0.
balancing factor of 14 now?
minus
0.
Huh?
Minus 1.
Minus 1. Minus 1 is the balancing factor. No problem. No problem, right? It is following AVL tree property. Then the next
Yes,
value is
sir.
11. 11, where I have to insert 11?
left side of 14.
Left side.
Left side of 14. Why? Because 11 is smaller than 14, na? That's why. Okay. Here I am going to insert, and 11 is at this position. Now, what is the balancing factor of 11? 0.
0.
And what is the balancing factor for 14?
0.
0, not minus 1. It is 0 now. Okay. It's balanced. It is balanced, no doubt. Then the next value is 7. 7, where I have to insert 7?
In the left side of 11.
In the left side of 11. Here it is going to be inserted. 7 it is inserted. And the balancing factor for 7 is 0. And the
0.
balancing factor for 11 is
1.
1. No problem, right? No problem. And what is the balancing factor for 14?
1.
That is also 1. No problem. Nothing is there, na?
Yes, sir.
Working very smoothly, right? Then the next value is 53. Next value is 53. Where I have to insert 53?
In the right side of 17.
17. No problem. Here also I have to insert 53. Here I am going to insert 53. Okay. The balancing factor for 53 is going to be 0. And the balancing factor for 17 is
minus 1.
minus 1.
Minus 1.
And the balancing factor for 14 is
0.
0. It is going to be 0. No unbalanced nodes is there. Up to this one is very good. To this one is very good, right? Now, after 53, what is the value? The next value is
Next
4.
value is 4.
4. Where I have to insert 4?
Left side of 7.
Left side of 7. Very good. I inserted 4 here. I inserted 4 here. Inserted 4. Balancing factor of 4 is 0. Balancing factor
0.
of 7 is
1.
1.
7 is 1. And what is the balancing factor of 11 now?
2.
It is 2. We observe it, it is 2. And it is 1. Okay. Now that means this is invalid node. Got it? This is
Yes.
invalid node. From this position, in what direction I inserted the new node?
Left
Left and
and
left.
left and left.
Left
Yeah.
and left. Okay. Left and left. If it is the left case, what we have to do? We
Right rotation.
covered left and left. Okay. We covered left and left. If it is left case, just simply we have to do one single right rotation. Yes.
Yes, sir.
If it is the right rotation, tell me what is the final output of this part,
Sir, 4 on the as a left child, then 7 as the root node, and 11 as the right child.
That's it. Na? Just simply we will delete this one. It is reverse like this, and just simply I'm going to delete it. I'm going to delete, and the new after rotation, it is working with 3 nodes. Okay. What is the root node?
7.
7 is the root.
7.
7 is the root, and 4 is no change, nothing. And this is going to be 10.
Fo-
10 or 11? 10 or 11? It is 11, na?
Sir, 11.
11. Yes. After the rotation, it is going to be like this. Okay, got it?
Yes.
And the balancing factor for all the values is going to be this is 0, and for this is 0, and for 7 is also 0,
Yes, sir.
and for 14 this is 1, 2, and it is 2, and it is also 0. No problem, right?
Yes, sir.
Yes. After 4, we have to insert 13. Where I have to insert 13?
Sir, on in the right side of 11.
In the right side of the 11. In the right side of the 11. Here I have to insert. Here I have to insert 13. Here I have to insert 13. 13 is inserted. Then we have to calculate what is the balancing factor of 13. It is going to be 0. And the balancing factor of the 11 is? Balancing factor of 11 is?
Minus 1.
It is minus 1. Good. It is minus 1. And the balancing factor for the 7 is?
Minus 1.
Minus 1 only. Minus 1 only. Yes. No other values is there now. It's working good. No doubt. Minus 1. No unbalanced nodes is there. Just simply it is good. Then 12. Where I have to insert 12?
Left side of 13.
Left side of
13.
13.
Left side of 13. Yes. And now I have to insert 12 at this position. Now I have to insert 12 at this position, right? Yes. Now it is 12. Now it is 12. And the balancing factor for 12 is
0.
0. And for 13, it is
1.
1. Okay. For this one is, for 11 it is
Minus 2.
minus 2. Why? Because there is no left hand part for 11, and it becomes minus 2 now. It becomes minus 2 now. Okay. Now, this is the unbalanced node. In what direction from this node I inserted the new node?
So first of all, right, then left.
Then left. Then left. Okay. This is a right left node. It is a right left node. First of all, we have to do right rotation on child.
Left
Right rotation. Then left rotation on 11. First of all, this will become, what will happen? 12 and 13. Right?
Yes, sir.
Then it becomes 12
So
is the
then it
root node.
becomes 12 will be the root node, left will be the left, 11 will be the left child,
Left.
and 13 will be the
13.
right child.
Right child. That's it. Yes, understand now, everyone?
Yes, sir.
Just simply I'm going to delete it. Okay. And it becomes like this. It is, there are 3 nodes. And what is the root node? It is 12.
12.
it is 12, and it is 11, and it is 11, and it is 13.
30.
13.
Understand how it is working? Yes?
Yes, sir.
How it is working? I am giving a simple task to you. After 12, 8, 8, 16, 19, 16, 20 is there. Just do remaining all the insertions. Here we covered two cases, left, left and right, left, I think. Yes? Just cover the remaining two cases also. That is the right, right is pending and left, right is also pending with this example. Okay?
Okay, sir.
And
Yes.
give me and write everything on the paper. Okay, first initially this is the tree, and if there is a small rotation, write another tree, go with another tree, step by step write, and take make it as a PDF, take the pics with a doc scanner and forward in the group. Yes, or personally, not at all a problem.
Okay.
Okay.
Okay,
This
sir.
is the simple task. If it is not understand to you, just go with again. I'm sharing this video again. I recorded the total thing. I explained each and every point very clearly in this video. If you pause it and stop and take another example and how it is working and everything, you have to prepare it own. Very clear, I think everyone, right? Yes?
Yes, sir.
Yes.
Yes. Yes, 10 minutes. This is the end of this session.